Welcome to Dimensional Data Modeling Day 3 lecture. Today we're talking about graph data modeling. Graph data modeling is significantly different than dimensional or relational data modeling in the fact that it is more relationship focused and less entity focused. So if you're looking at how things are connected, that is going to be where graph data modeling truly shines. But it comes with a trade-off where you don't really have as much of a schema around the properties. So the schema in most of the graph data modeling is very flexible. It just has like a vertex and properties or an edge and properties. The schemas are very, very flimsy and flexible. And so I worked a lot with graph data modeling when I worked at Netflix. We built graphs that had 70, 80 different types of things in them so that we can understand how everything is connected. And you might end up ultimately loading the stuff into like a graph database. But in today's lecture, we're going to be talking about just the data layer and how to build a data agnostic graph data model. And I hope you enjoy the lecture today. And if you want to learn more about how to build graph data models in the cloud with hot technologies like Iceberg and Trino, definitely check out the Data Expert Academy in the description below. Okay, so today we're going to be talking about a couple things here. We're going to be talking about additive versus non-additive dimensions, which is a perplexing little concept that I'm definitely going to help illustrate here. Then we also have the power of enums and enumerations. We covered a little bit about enums in day 1 and 2. Remember the scoring class, right? I need to mute people. I'm getting some echo. I think it was Thinagar. Can you mute yourself? And then we're also going to be talking about when you should use flexible data types. Like in this case, flexible data type is only counts for map. Map is the only one that's flexible. Struct is not flexible because you have to define all of the keys and all of the data types of everything in the struct. And array is kind of flexible because you can add more things to it. But usually array has to be an array of string or an array of a specific type. And whereas map can have keys and values that are all kind of you can have as many as you want. A lot of times map string is a very powerful thing because it's agnostic and you can create all sorts of interesting data with that. We're going to go deeper into all of these topics, so don't worry about it. But first off, let's get into to additive versus non-additive dimensions. Okay, additive versus non-additive. So this mostly is when you're talking about how to count stuff. You are able to essentially take the sub counts and you can add them all up. If you take all the subtotals and sum them up, you get the grand total and you get the correct number. So for example, in the US, if you take all the 1-year-olds plus all the 2-year-olds plus all the 3-year-olds plus all the to all the 115-year-olds and you add all of them up, and you just know the size of each group. You know that you can just add all the sizes of each group together, and then that is the correct number for the grand total. But not all dimensions are like this. For example, I like this example around cars. So say you have the number of Honda drivers. The number of Honda drivers is not equal to the number of Civic drivers plus Corolla drivers plus Accord drivers, and the reason for this is because what if I own a Civic and a Corolla, right? Then the problem here is I'm going to be double counted because I'll be a Civic driver and a Corolla driver. I'll be in both buckets. So, but you don't want to double count me. That I'm just one Honda driver. I shouldn't count as 2 Honda drivers there. Whereas if you slightly tweaked this, right, instead of the number of Honda drivers, you say the number of Honda cars, then you're fine because a car can't be 2 cars at the same time. But a driver can drive 2 different cars at the same time or in the same day. And so that's the essence here of additive versus non-additive is can an entity have 2-dimensional values at the same time over some sort of time frame? And that is going to make more sense as we go deeper into this. Okay, so the essential nature of additivity. A dimension is additive over a specific time window if and only if the grain of data over that window can only ever be one value at a time. This is like, I know this sounds very like mathematical, very like, I even got the if and only if in there, the biconditional statement. So, for example, like say we go back to the Honda example. So on a small enough time scale, you could say that the number of Honda drivers is equal to the number of like Civic plus Corolla plus that, right? Because imagine if you looked at just a slice of 1 second, right? And then in 1 second, like I can only be the driver of one car. I'm either going to be a Honda or a Corolla driver or a Civic driver, but I'm not going to be both because unless I'm like able to like switch cars in 1 second, which is probably not going to happen. So on a small enough time scale, that dimension is additive. But once you get it to a big enough time scale, it no longer is additive. And so that's a big thing to remember here is like how these dimensions interact with time. That is a big deal on like how to think about the nature of these as you aggregate and roll these up. So that's this problem comes into a place in a couple places. One of the key things that it's on this slide. Cool. So how does additivity help? So how additivity helps is if you have the subtotals and if you know the dimension is additive and you have the subtotals, you can just add them up and you don't have to use count distinct. Because if you have to if you're trying to do it the grand total and the dimension isn't additive, then you have to go back, right? You have to essentially do a count distinct over the entire data set as opposed to the subtotal data set. You have to essentially go back. You have to go down a layer. You can't have that a partially aggregated data. You have to go all the way back to like the row level data to get the grand total because you don't know how much of the data is being overlapped between like, the Civic and Corolla drivers. Is it 1? Is it 2? Like how much overlap are we talking? And so one of the things that's interesting here, though, is this really only applies if you're aggregating it with a count. Because if you're aggregating a sum, like, for example, if you're saying the number of miles driven by Honda drivers, then you're fine because you can say the number of miles driven by Honda drivers is equal to the number of miles driven by Civic drivers plus the number of miles driven by Corolla drivers. And it all adds up. It all makes sense, right? Because I can't drive a mile in 2 cars at the same time unless I'm like freaking Superman and I'm like steering one car with my feet and like steering the other car with my hands, right? And doing some crazy shit. Like I mean, for all intents and purposes, we're going to say that that's not possible, right? So really additivity and this nature only really matters for count. But because it matters for count, it also matters for other types of metrics as well. Right, and the big other type of metric that it applies to besides count metrics is when you have a ratio metric, right? So imagine you have the number of miles driven per driver. Then you're back to a metric that is non-additive, right? And you're going to have to like deal with it, right? If you compose these metrics together, then you're still back into the nasty additive versus non-additive thing where you have to worry about count distinct versus not count distinct. So remember the key thing here when you're looking at these dimensions to know if they're additive or not is, can a user be 2 of them at the same time? And usually like a rule of thumb here is like, can a user be 2 of these at the same time in a given day? And if they can, then it's not additive, and you have to deal with it. You have to deal with it differently. You can't do like the partial aggregations like you can with other dimensions. Good news is like most dimensions are additive. Like I would say there's only a couple. Usually these dimensions are going to be like I like to think of it as like a tool, right? It's like a user's tool, right? Another great example is like you can't say the number of users on your app is equal to the number of iPhone plus Android users because of the fact that there's some people out there that are on both iPhone and Android. And so it's like, you see how that's like a user's tool, just like a car is a user's tool, and it's something that a user uses and you can aggregate along that dimension. And that's why you get 2 values. So that's definitely something to think about when you are doing these aggregations. And like this was such a big problem at Facebook that like we actually built frameworks around this so that people didn't have to worry about this problem anymore, and that like if they wanted to do a non-additive aggregation, they can do it like efficiently through our framework. And that was we built this thing called Milky Way, and like that was a painful little process that I noticed that I like this problem will show up. So definitely just like do more research on this. We're not going to cover much more about this in the lab, but this is an important topic in terms of analytics and growths, especially like user counting in growth analytics. This is a very important topic to consider. All right, so we're going to shift gears kind of completely here. So we have enums, right? So we covered enum in the last class. Remember the NBA scoring class, like star, good, average, bad. Like we had those kind of different enumerated fields that we were working with there. And one of the things that you'll notice with enumerations is there is a limit, like to how much you want to enumerate. Like, and I love country. Country is always a great example because country is one where like some junior data engineers might be like, yeah, we should throw country in an enum, and it's like, nah, dog, that's too many. That's too many. That's like 200. Like, I always think of like a good rule of thumb here is like, is it less than 50, right? If it's less than 50, it's probably a good idea, right? That's where we're going to be covering how enums can be very powerful in different data architectures in this class as well. Let's go to the next slide. So why should you use enums? So a couple reasons. One is you get built-in data quality, like for free, essentially. Because if you model a field as an enum, if you get a value that doesn't fit in the enum, then the pipeline fails. Usually the pipeline will fail because it's like we're trying to cast this value to this enum and it doesn't exist. So you get very good data quality in your pipeline, like automatically. Other things that you can get is you can get built-in static fields. Because sometimes there's fields of an enum that are just static that you need to know about, right? For example, like in unit economics, like I had an enum for all of the different line items. And one of the static fields was this a revenue or a cost? And that is just like, okay, each line item, like fees are a revenue, right? And coupons are a cost. And there's like all sorts of different like static fields that you can also apply to enums. And the good thing about those is you can bring those in a more efficient way than even like a join, like a broadcast join, because of the fact that they're just like in the code already. And it's like you can just bring them, you can ship the enum and all of the static fields with your code. So like it can be very, very powerful way to do it. And another big thing is you get built-in documentation, because now if you have a list and you know what all the possible values of that list can be, that is another really great thing, because that shows people like, hey, I know what are the possible values here and I know what I can do. And whereas like if it's a string, that you don't get that, right? You don't get the possible values when it's a string. And so that's another great thing you get is built-in documentation. So enums can really up-level your data quality, keeping in mind that you don't want to just throw it on anything. Like you want to make it so it's like if it's something that has 50 or less possible values, that's like a good rule. Like for example, one of the enums that we had at Facebook was in notifications. There was we had this notion of a channel. A channel was like how we sent someone a notification, which was like either SMS, email, or push. And there was like one more. There's also one that was like logged out push, which is like a different channel, because some people like in the developing world, they actually share phones. And so they get like Facebook actually has things set up where you can get notifications when you're logged out for a different user. Because if you have someone who's like sharing a phone, and that actually like really helped increase engagement in notification or like for Facebook in the developing world. But like when you think about that from like the United States perspective, you're like, whoa, that's crazy. That's like a crazy like we would never do that in the US, right? That sounds like a privacy concern or something like that. But like different countries have different expectations there, especially like when they're like sharing a phone. But so anyways, enums are great, and they can model things really cool. So one of the amazing things that can happen is with enums is they can be a good value for your subpartitions. So if you say like in notifications, again, like when I was processing notifications, like you don't want to process all the notifications together because it's like a lot. So instead of just partitioning on date, we partitioned on date and channel. So there was also the channel column there, which was, and that's why enums are so powerful, because if you have the exhaustive list of all of the possible values for a partition, then you can build a pipeline that covers everything and it waits and actually gets all the possible values and it doesn't miss any data. And that could be another really great thing to remember when you're like working with this stuff. So when I was like doing like my notifications dedupe work, that was the case where we essentially deduped notifications by channel so that we could do them more in parallel as opposed to having to dedupe all the notifications together. And that can be a very powerful thing, especially if you move up a layer and you are pushing this into like the logging layer as opposed to in your ETLs. Because then what you can do is, if y'all have ever heard of Thrift, Thrift is a very powerful thing that you can use. So Thrift is a way to manage schema in your logging as well as your ETLs, and you can share the schema across the board, and you can share enums, you can share all sorts of different things through Thrift. And that's a very powerful way so that like the logging and the pipeline are on the same page in terms of what the enum values are. Because sometimes the enum values will change, right? You'll add one, right? Or you might even remove one, right? And depending on the case and the circumstances. So that's a very powerful thing to think about. This other big thing, I'll share these slides after this, but like I came up with this design called the Little Book of Pipelines. That is a very, it leverages this concept of enumerations to a great extent. And this design I've used a bunch of times. I used this design at Netflix to do like the asset inventory stuff, and at Airbnb to work on unit economics. Essentially like this enumeration Little Book of Pipelines pattern. If you ever have a pipeline that you're working on that really pushes that the variety V, where there's like, wow, like this pipeline has 50 upstream data sets. Like, how do I manage all of these data sets? That's when you want to group those data sets into an enumerated group. So then you have like all the groups that could possibly run. And then that is how you keep track of all the possible values of stuff. And that is what the Little Book of Pipelines actually ends up doing. And we're going to talk about that more on the next slide here. Let's talk about how this works. So you have a source, all these different sources here. So imagine like these there was not just 3. You can have n number of sources. This essentially works kind of infinitely. So what this does is you have an enumerated value, right? That has some sort of set of values in here. Like, for example, at Airbnb, there was like maybe fees and coupons and infrastructure cost and all the different things that impact profitability. And those all go down the side here. And you have all the source data that you get that from. And then how it works is this enum gets pushed into these source functions. It gets shared with all the source functions. And then these source functions, what they do is they map the data to a shared schema. And the way they do that is this shared logic ETL will call the source function, and then it will map it over into the shared schema. And then after that, the Little Book of Enums also has the data quality checks for that enumerated value, because your data quality, even though now the schema is shared, that doesn't necessarily mean that the data quality check should be shared, because like what is anomalous for fees and what is anomalous for coupons is probably different. And so that can be a very big difference that you can think about. And that's where this little book can be very powerful, because what it stores is it stores all the enumerated values, all the data quality checks, but then it makes it so that like even if you have a shared schema, you can have customized data quality checks on each partition depending on whatever's in that little book. And then after the data quality checks pass, then you have your final sub-partitioned output. And this partitioned output it'll have a date partition, and then it will have a sub-partition, which is this enumerated value, whether that be like fees, coupons, or something like that, like some sort of enumerated list of things that could possibly be in here. So this pattern works at like, especially if you have a massively large ETL that like covers a lot of different topics, and and they all need to come together into one shared schema. This is a very, very powerful design that I've noticed that really makes it easy to keep track of things. Because then if you need a new source, you just add another value to the enum, done, easy, right? And then you get your DQ checks, and then you just have to add the source function, and then everything else will just work. And then it all is very cohesive and integrated. And I've noticed that like when you implement this pattern, what happens is the quality of these pipelines goes up dramatically, and you get and you also get this documentation for free, because now people can be like, oh, what are the possible partitions in here? And you just query the little book here and you're done, right? And it's pretty great. So how that little book actually is generated, right? So it's usually going to be an enumeration defined in either like Python or Scala. But then what you have a job that essentially turns that enumerated list into a table, and that table will be tiny. It'll maybe like 20 or 30 rows or 40 rows, however many values in the enum you have. And then that's how you can share it between like your DQ checks and your source functions, where in the source functions, you pass it as Python. And then in the DQ checks, you pass it as a table and you join. And that's how you get like your thresholds for like week over week, month over month, stuff like that. And keep in mind that like there's a lot going on with this pattern, and so like I highly recommend that y'all check out this example. There's something it's an open source library that or open source like GitHub repo that I shared that y'all can check out after this presentation. So let's go into this a little bit more. So like, what are the use cases for this little book of enums? So I've seen it happen a couple different times, right? Earlier I was talking about Airbnb. They have unit economics where it has all these enumerated fields: fees, coupons, credits, insurance, and infrastructure costs, taxes, referral credit. There's so many more. And then Netflix also with the infrastructure graph that I worked on. In that case, you have like applications, databases, servers, code bases, CI/CD jobs. You just have this like big list of things that you need to put together. And that's kind of the idea behind this pipeline design, is that if you ever have this like, I call this like large scale like data integration, when you need to like just bring tons and tons of data together into one table. And then also this, I saw this at Facebook as well for the family of apps, where in that case you have like Oculus, Instagram, Facebook, Messenger, WhatsApp, and probably Threads now. I don't know if y'all are on Threads. You should definitely follow me on Threads. I post some spicy memes on Threads. So those are kind of the use cases, right, that I've seen in my career, and they've all been very impactful. They've all like changed the company in some way or another. So definitely, I highly recommend checking this pattern out because it can be very, very powerful. Okay, so one of the things that I was talking about in this pattern, though, if you remember back here where we have that shared logic and that shared output, what this ends up being is you end up having a pattern where all of the data ends up being in the same table. So how do you model data from disparate sources into a shared schema? So it's tricky. And the main way that you do this is with what I call a flexible schema, because like you don't want to just like bring in all the columns from all 40 tables and you just have like one table that has like 500 columns where most of them are null all the time. Because that's like not a very usable table, right? And you don't want to work with stuff that way. That's definitely not the way that you want to like bring the data in. What you want to do instead is you want to work with what I call a flexible schema. And this flexible schema is where you're going to leverage a lot of map data types here. It's going to be the big one that you use to do things. And a lot of this stuff is going to overlap a lot with that kind of graph, that graph database I was talking about, because the enumerated list of things is very similar to like in the graph database world. We have this thing called a vertex type, right? And that is very similar because it's just like an enumerated list of types. And so these concepts are integrally connected. And so like let's talk more about flexible schema. So flexible schema is awesome because if you need to add more things, you just put it in the map, which is great. You can just throw more columns in the map. Like if more columns appear, you can just throw them in the map. That's awesome. That's a great, and then the map can just get bigger and bigger and bigger. There is a limit, right? I think maps like in like Spark and that world, I think they can have like 65,000 keys. Like, so there is a limit. There actually is like a fundamental limit, but like I've never had that many keys in my map. I've maybe had like 1,000 keys in my map at one time, but like never like 65,000. That's like it's an aggressive amount of keys. So that's like, and that limit comes from the byte length or some sort of Java limit, right? So you can manage a lot more columns when it's flexible, right? Because you can just add another key to the map and you don't have to run alter table. It's great. You don't have all these null columns because a lot of times, like with flexible schemas, it's just going to not be in the map, and so it just doesn't show up. Another good thing that I've seen a lot of like companies do is they have this column called like other properties, where if you want to bring more columns into the table that are probably not going to be queried that much, so you don't actually want to do the modeling of them, because like why bring them in and get all these weird questions about like what does this column mean? Like what they do instead is they just throw it into other properties and then they call it a day. Really great. Obviously flexible schema, if like it was all good, then we would just be using flexible schema for everything. It's not all good. A very big drawback is compression. So if you throw everything into a map, maps are going to be pretty much the worst compression of all the data types. The only thing that might be worse is JSON. JSON and maps are both really terrible. They both are like very huge and they don't squish down very well. And the main reason for that is that you got to think about it like where in the old world, like if you have a column header for every column, that's great. And then the column header is only listed once. But if you put it in the map, now the header is in every single row. So, and that's stored as data. So the header is now data instead of being just part of the schema. And that is one of the things that really greatly increases the size of the map and the flexible data types. So definitely think about that when you're trying to work with this stuff. So yeah, how is graph data modeling different? Graph data modeling is relationship focused. It's not entity focused. So like a lot of these columns and things like that you would find in data tables are just freaking not there. I'm about to give you the super secret sauce to all graph data modeling. I hope y'all are ready for this. It's very, very easy, because every graph database that I've made like probably 3 or 4 graph databases now in my career. And they all have the same schema, always. And it's weird. It's like spooky how they all have the exact same schema. So like just if you can remember this schema, then like you essentially have your graph data modeling skills mastered. So the main thing to remember about graph data modeling is that it's not entity focused. So we don't care about columns. We really don't. So really for an entity in a graph, you have 3 columns. You have an identifier, you have a type, and then you have properties of that vertex, right, or that node. And so in this case, like in our examples today that we're going to be working on, we're going to have a type which is like a player type, and then the identifier will be their name, and then in the properties might be like their height or their weight or their draft year and things like that. So we're definitely going to be working with some of those, and we will be building that out. But keeping in mind that like this schema is exactly the same for like the family of apps, right? For example, like you would have a user ID, and then it would be of type user, or it might be of type WhatsApp user or type Instagram user. And then you have a graph that maps all of these properties over to each other and how they're connected, because maybe this Instagram user actually has a connection to that WhatsApp user because they're the same person. And there's a relationship between these 2 nodes. And that's what we care about. We care about the relationships. We don't care about the entities themselves as much. And that's like the whole idea behind graph databases, is like it's shifting the focus from how things are to how things are connected. And if you can remember that, you're going to do a lot better in your graph data modeling just experiences. So yeah, let's go to the next slide. Okay, so in that case, remember for vertexes, you have that 3-column schema. Edges have their own schema, which again is pretty much standard. This schema is very standard, where you have your subject identifier, subject type, object identifier, object type, edge type, and then properties of that relationship. Like, for example, like the edge type is almost always like a verb. Like, it might be is a, or plays with, or has a, or different things like that. It's like a one or two word like sentence. It's a very simple thing that like connects things. Like, for example, in the lab today, we're going to look at like how players in the NBA play with each other and against each other. So you have like plays with and plays against. Those are two different columns that we are going to be generating, or two different edge types that we are going to be generating in today's lab. And so if you look at the different things here, like, I like to think of subject and object as like a sentence, right? Where the subject is the person doing the thing, and then the object is the thing is being done on, right? Like, for example, we are also going to be creating a relationship between a player and a team. So it would be like, player plays on team. And so in that case, you would have the subject identifier would be a player name. The subject type is going to be player. The object identifier will be a team name. The object type is a team. And then the edge type is plays on, or like that's going to be they play on that team. And then the properties might be like, how many years did they play on that team? When did they first start playing on that team? Things like that, right? There'll be these different properties of that team object that we'll be working with. So that's kind of the idea behind edges. So you have nodes and you have edges, and they are connected, right? The way they're connected is an edge takes two nodes and links them. And it links them through some sort of type, some sort of edge type, and then they're linked together. That's the whole point of graph databases, is looking at how things are connected. So let's look at an example here real quick. So we're going to be building out this exact graph database in the lab today. But you'll see like you have like Michael Jordan and John Stockton. These are two like kind of famous NBA players who played against each other in like the 1990s in the NBA finals. And they play against each other because they're on different teams. But then you'll see that like John Stockton is connected to the Utah Jazz because he plays on the Utah Jazz. And so this is exactly what kind of modeling you're going to expect when you are building out graph databases. Is you have you have your subjects, you have your objects, you have your connections, and then they might have properties inside of them. But this is the idea, is like you're really focusing on how things are connected. And this is how you can build out these kind of models. And like you can build out really, really cool insights from this, because a lot of the stuff, like when you are in the other world, when you're in that kind of like relational database world and you're not in this graph world, a lot of the times like the queries that you're trying to do, like these graph traversal queries, they get messy because like you have to join and you have to create all these like crazy joins to like do it. And you have to bring all the vertex data together and do all these like crazy extra scans. But like once you get the data in this format, then you can start traversing the graph and seeing how things are connected in a lot more of an efficient way. And that was a big thing that, like, when I was working at Netflix, that was a big thing I worked on, was like, how do I get all of these different entities into a singular graph database that then people can query and people can like look at. And that was, it was fun. It was a really fun problem, but also a very challenging problem because it just gets super messy. But that's kind of the idea behind how graph databases kind of work. All right, so I think that's pretty much it for the slides today.